Hello. All right. Let's check out chapter 2. If any of you have ever taken chemistry, some of this will be familiar to you. For some of you that have never taken chemistry, don't worry. Okay, I will get you through this. I've taken chemistry many times. I've taught this course for many years. All right, so I'm pretty familiar with the material. Just to let you know, the first time I ever took chemistry was in high school, and I failed it. Not to fear. I went back and took it in summer school, got a B in it, and then went and took it in college and got straight A's. And then I took organic chemistry. So I want you to understand that chemistry can be overwhelming, but this part of the chemistry that we're going to be going over, the biochemistry, is going to be pertinent to this course. And so we're really going to help you along with a general understanding of that. No. The worksheets are not useless. Trust me, they are not useless whatsoever. Okay. The publishers have included those. They will be very helpful in learning the material. There is nothing that is useless in this course if it helps you to learn the material. Okay. What works for some might not work for others. Okay. So again, don't never apologize for asking questions. I love questions. All right, but if you think that you could benefit from the worksheets, by all means, use the worksheets. Again, you want to be able to manage your time though, and make sure that you are completing whatever assignments that are required of you in a timely fashion when they're due. And then also make sure that you know that you're utilizing the materials that you have available to you, and some will work better for you. Now, I send out the Quizlets to you folks because some folks like the flashcard method of learning structures. And I mean, I love it. What I love about it is, like I said, you could be sitting waiting in the dentist's office. You got 10 minutes to kill before you have to go in and get your teeth cleaned. You can pull out your phone, open up the email that I sent you, click on the link, and bang, there's Quizlet. And you can roll through about 10 to 20 slides. Good. And I'm going to keep rolling those out. Okay, now there's maybe 2 chapters, I can't remember, that I don't have Quizlets for. I'll let you know. I want to say it's one of the bone ones. But trust me. Oh yeah, the practice matching is great too. Drag and drop. That is a phenomenal exercise to do. I'm telling you folks. We really kind of stepped it up this semester because we didn't have some of those resources. Well, at least a lot of the time when I was teaching on campus, I didn't have to use some of these resources to present to the students because we were having more of a face-to-face interaction. But I would definitely utilize all that stuff. It will be very helpful for you. Okay, so let's jump on in here and talk about molecules and atoms and ions in the periodic table and all this fun stuff. All right, so when we're talking about biochemistry, one thing we have to understand is we're going to be dealing with matter, specifically organic matter. Right, and organic matter is anything that has a carbon molecule inside of it. All right. And so when we're dealing with matter, matter has 2 components: mass. Some people refer to that as the weight, how much something weighs, and also volume. So matter has to have mass and it has to occupy space. And there's 3 forms. And I've seen this before. So this is a great test question here. What are the 3 forms of matter? Okay, solid, liquid, gas. And you can see how it compares. All right, solid could be bone. It could be cartilage. All right, liquid is blood or lymph. All right, or even it can be fluid like water. Gas are respiratory gases, oxygen and carbon dioxide. There's nitrogen in your body also. All right, so be familiar with the 3 forms. So again, when we're talking about with chapter 2, we're dealing with the overall organism is our end goal to refer all this material to. So we're going to start off on the simplest level. And so we're going to start off by talking about the smallest particle, and that's an atom. And there are atoms are the smallest particle that we're going to deal with in this course, but they are part of something a little bit bigger, which we call elements. And there's 92 natural occurring elements, all right, that are known so far to us, all right, that make up all matter that we're familiar with. So the nice thing about the atoms is going to be this one principle is that this, even though the atom, it's the smallest particle of an element, like gold, for example, it's going to have all these chemical properties and these different types of physical properties that will relate to the overall element itself. And we'll talk about that in a moment. All right, good news is for those of you that are familiar with chemistry, and you probably heard about the periodic table, don't worry, you don't have to learn the periodic table. I'm going to just talk you through a couple things on the periodic table. In fact, I don't even have a periodic table in the slideshow. Okay, so don't worry about the periodic table. All right, so here we are talking about atoms, all right, which is the simplest level of our organization that I was discussing with you earlier. And there's a couple terms here that you need to be familiar with. One is atoms. Okay, you already heard me mention that. It's the smallest particle that we know of, all right, that exhibits chemical properties of whatever element that it's associated to. Then we have ions. Now, for right now, you just need to know that ions are charged particles or charged atoms or groups of atoms. Okay, we'll get into the whole plus or minus later on. And then if we stick a couple atoms together, then we get molecules. And we hold these atoms together, all right, through bonds. And we're going to discuss the different types of bonds. Okay, we have some ionic bonds, all right, we have covalent bonds. We're going to discuss all these different types of bonds. Okay, but for right now, let's refer to these bonds as chemical bonds because we're going to be dealing with different chemicals. So it's very important, especially when you get into 211, that you have not just a basic understanding, but a very strong understanding of these chemical concepts, because it will help you to understand some of the physiological processes that we are going to learn in this course. All right, especially when we get into the nervous system, we're going to be hitting some a lot of different kind of molecular movements in these cells, and it can be difficult, but trust me, I'm going to do my best, walk you through this, okay, to help you to understand, right, as much as I possibly can. We're going to do this. We're going to do it together. So here we're looking at the most common elements that reside inside of all of us. And so on the left side of the screen here, you see the major elements, and they make up 99% of your body weight. And then the remaining 1%, we call those the minor elements. You need to be familiar with all of these. You especially need to be familiar with these four. Okay, they make up a majority here of your body weight. If you look at, oxygen makes up 65%. Now, granted, a significant amount of your body is made up of water, okay? But if you see there, the second, all right, major element is carbon, and it makes up 18.5%. So there's a big difference between oxygen and carbon. All right, so when you look here, you'll notice on our slide, when we're talking about these different elements, we're talking of, you can see here, we have these symbols that represent these elements. So you need to be familiar with these symbols, all right? Those are going to be the symbols that we're going to utilize to represent, all right, the elements that we're discussing. Now, the major elements are pretty simple. Oxygen starts with an O, carbon with a C. When you get over here to the minor elements, if you look at potassium and sodium, all right, and even iron, okay, those three, you notice their symbols are a little bit different. That's because we're using the old Greek nomenclature. So we represent potassium with a K, sodium with an Na, and then iron is going to be Fe, which is ferrous. All right, point being is that's something you're just going to have to memorize. You just got to know it. Okay, so if I write on the screen here, K plus, then you should know, oh, Dr. Kaz is talking about potassium. So you need to just kind of memorize that. For the most part, it's not too difficult. All right, so let's talk about all the parts to an atom. And so atoms, when you're thinking about an atom, I want you to think about our universe, all right, our solar system, I should say. So our solar system has the sun at the center, and the planets circle around the sun. And so atoms are very similar to that. There's a structure at the center of the atom. We call that a nucleus. And then we have these smaller structures that circle around that nucleus. And we're going to talk about that. All these components we call subatomic particles, and there's three types. I'm not going to be getting into the really small particles like quarks and all that. All right, let's keep it simple here. So in the center of our atom, here's our nucleus. We have 2 out of the 3 subatomic particles. The first one is the neutron. So we write an N for that. Think of a neutron as being neutral. It has no charge, but it does have weight to it, or mass. And so when we're dealing with subatomic particles, we use a specific unit called atomic mass unit, or AMUs. So a neutron has a mass of 1 AMU. Well, the nucleus is shared, all right, between the neutrons and the protons. That's the second subatomic particle that resides inside the nucleus. Now, it also has a mass of 1 AMU, but here's something special about it. It has a positive charge, +1. So think proton, positive. So if you have 1 proton, you have 1 positive charge. If you have 2 protons, you have 2 positive charges, and so forth and so on. Okay, so at the center of our nucleus, you can see here we have 2 subatomic particles. And then circling around in an orbit, like a planet does around the sun, we have the 3rd subatomic particle, and that's called the electron. Now, the electron has a charge of -1. So 1 electron has 1 negative charge. 2 electrons have 2 negative charges. But electrons are far smaller than protons and neutrons. In fact, they're 1/1800th the size, all right, or the mass of a neutron or a proton. So they barely contribute any mass to an atom, hardly any. But the big thing is I want you to understand is they reside in the orbitals, not in the nucleus. So they circle around. And so these orbitals are found at different distances from the nucleus, much like in our solar system here. Okay, Mercury is closer to the sun than we are. All right, so just like there's many different orbitals around our sun, an atom can have several orbitals around it that go further and further and further and further away from the center, from the nucleus. Okay, so we've mapped out and we've discovered all these elements. So of course, being good scientists, we need to write everything down. So we did. And we generated this thing called the periodic table. And so we were able to put all these elements into these organizational positions on the periodic table to better explain their qualities. And so if you look at a periodic table, it has all these numbers scattered all over the place. Excuse me, not numbers, letters. Again, those letters are the chemical symbol and they're unique to each element. So like we saw earlier, on that previous slide, okay, we saw that C represented carbon, O represented oxygen, K represented potassium. So you'll have all these elements represented by those chemical symbols. And also, okay, when we're dealing with, okay, these chemical symbols, all right, so let's do hydrogen. It's the simplest one, hydrogen, H. There's the chemical symbol. Now, next on this slide here, you see atomic number. Now, the atomic number tells you the number of protons in that element. And so that's written as what we call a superscript up here. So hydrogen has 1 proton. So it has an atomic number of 1. And then below it, we'll see another number, which is going to be larger than the top number, because that's the atomic mass. How much does this element weigh? And so what we do is we add both protons and the neutrons together to get the atomic mass. Okay. Normally, the number of protons equals the number of neutrons. In some cases, it won't, and I'll show you in a moment here. Okay. So if hydrogen has 1 proton, that means it also has 1 neutron. So its atomic mass will be 2. And that's what we'll see, amongst other things, on this periodic table. So when we're trying to figure out, all right, the number of how many subatomic particles exist, all right, in one of our elements, here's a couple of ways that we can figure it out. Okay, I already mentioned the atomic number. The atomic number tells you how many protons you're dealing with. Okay, and then you can also figure out how many neutrons there are by taking the atomic mass. So we'll use hydrogen again, keep it simple. Okay, 1 and 2. So if we want to figure out how many neutrons there are, you take the atomic mass, which is this lower number, and you subtract the atomic number from it. So 2 minus 1 is 1. So we have 1 proton and 1 neutron. Now, like I said, normally this is the case, but in some elements, that's not the case. Like sodium, for example. Okay, you can see, all right, its atomic mass is 23, but its atomic number is 11. So if we subtract, all right, the number of protons from the atomic mass, we get 12. And so that means we have 1 more neutron than we do protons. And for the most part, your electrons should equal the number of protons that you have, unless we're dealing with a charged particle, an ion, but we're not talking about that yet. Okay, so if we look at sodium, okay, sodium Na has an atomic number of 11 protons, an atomic mass of 23. Okay, what did we say here at the bottom? The atomic number is the number of protons. And so at the bottom here of our screen, okay, the number of electrons should equal the number of protons. So our atomic number is 11. That's our number of protons. Then we should say, okay, well, the electrons equal that. So we have 11 electrons in a neutral element. Okay. So let's discuss how we're going to draw all this out, because I'm going to be drawing some things here and I want you to understand. So we're going to use the shell model. Now, for those of you that have taken organic chemistry, there's also the cloud model, right? But we're not going to be using the cloud model. All right, that's too much. We don't need to get involved in that. If you want to get into the cloud model, go back to organic chemistry. Okay, we're going to use the shell model. And this model is how we draw out, all right, our atoms. So like I said before, think of it like our solar system. Okay, at the center of our atom, we have our nucleus. That's where the protons and the neutrons live. And then circling around the nucleus are going to be where our electrons live. Now, if you notice here on our diagram over here, you can see that there's 2 orbits, one close to the nucleus and then one that's further away. All right. So each of these orbitals or shells has a specific amount of energy inside of it, and it varies. The further away you get, okay, the weaker the attraction for the electrons are to our nucleus here. So these shells or orbits can only hold, all right, a certain amount of electrons. So commit this to your memory. This next statement, the innermost shell, the very first shell, it can only hold 2 electrons. That's it. If you look at the shell model picture here, see those 2 yellow dots at the bottom of that first orbital? Okay, those are the electrons. That's it. There's no more that shell can hold. So what we'll see is, and here we have a second shell. Okay, it presently has 6 electrons. But this shell happens to be known as the valence shell. And that means it's the outermost shell. Okay, so if this model had 6 rings around it, the outermost ring or shell or orbital is going to be called the valence shell. And the valence shell, the maximum number of electrons that it can hold is going to be 8. So in this model here on our page, it has 6, but it can hold 2 more electrons before it fills its valence shell, the outermost shell. Oh, and last one here. Okay, if we're going to start adding electrons to our shell, to our atom, okay, the shell that is closest, or the orbital that's closest to the nucleus, has to be filled first. Then, once we've filled that orbital, then we add another shell, and we start to fill that one up. And when we get to 8, okay, then we add another shell, and we start to fill that up. Okay, that's how it works. We're always going to fill the shells that are closest to the nucleus up first. So when we're looking at the periodic table, now I told you I'm not going to put a periodic table up here, right? But I want to kind of give you just a quick idea of the general structure of the periodic table. So when we're looking at the periodic table, we're going to have rows that go from left to right. And then we're going to have columns that go from top to bottom, or bottom to top, whatever. Okay, up and down. Okay, so those are rows. So the first row, or what we call, excuse me, not row, the first column is 1A. That's going to be right here. And then our last column, all the way to the right, all right, that's going to be that B11A, okay? So the first column, column 1A, is only going to have elements that have 1 electron in their outermost shell, the valence shell. So the smallest one will be here at the top, and then as we move down, they get a little bit bigger. All right, but as we move from left to right, we are going to increase the number of electrons that are going to be in the valence shell until we hit the number 8. So basically, it goes from 1 to 8 when we're labeling the columns from left to right. And so as we move from 1 all the way to 8, we are increasing, or actually gaining, what we call chemical stability. Nature loves stability. It loves balance, okay? It loves things to be in order. Well, I shouldn't say it like that, because it also does like chaos, okay? But it does love, when we're talking about chemicals, all right, when we're dealing with these electrons, they want stability, which means the more electrons they have in the valence shells, they start to get closer to 8, because once they're full, once there's 8, it's like someone stuffing their face and getting full from eating, then they're satisfied. So in this situation, all right, once our element, all right, our atom has gotten 8 electrons in its valence shell, it's reached chemical stability. And then we refer to it as being inert, and chemically inert, which means it's non-reactive. It's not going to really do a lot and mix around. So we call all those elements that sit in that last column noble gases, helium, neon, and whatnot. Okay, so they're chemically inert. They're just not very reactive. So when you have chemical stability, all right, you're not going to be very reactive. If you have chemical instability, you'll be more reactive. All right, let me take a quick swig here. Let's talk about chemical compounds. So now we've kind of got a little introduction into our atoms and what they are. So we're going to start to talk about chemical compounds. And there's 2 types of chemical compounds that I want to discuss with you. All right, ionic and also molecular. But when we create these chemical compounds, what we do is we take a couple of these elements, a couple of these atoms, and they will actually interact with one another and create these stable associations. So when we talk about chemical compounds, we're creating stable associations between 2 or more elements, all right, combined in a fixed ratio. Well, what does that mean? Let me show you. Let's talk about water. Everybody knows water, right? H2O. Okay, so here you can see, I'm writing it out for you. This is the molecular formula for water, H2O. So when you're looking at this, all right, we're using the letters, of course, to identify, those are the symbols, whatever elements we're dealing with. So H is hydrogen, O is oxygen. And then the subscript here, the number is telling you how many hydrogen are present in this compound. And if you don't see a number here after the chemical symbol, it's always understood to be 1. Okay, so H2O means you have 2 hydrogen and 1 oxygen. And so that's what we're discussing when we're dealing with a fixed ratio. So for every 1 oxygen in the water molecule, you'll have 2 hydrogen. So let's start off. I want to talk about ionic compounds, because ionic compounds are going to create crystals or this lattice type of association. We're going to talk about table salt here in a moment. So first, in order to understand that, we got to talk about what an ion is. And I mentioned it earlier. Okay. So I said before that ions are a charged particle. Now we're going to get more specific. An ion is an atom that has either a positive or a negative charge. So it's positive or negative. Okay, so in order for that to happen, that atom has to lose or gain 1 or more electrons. I want you to think that the only thing that can come and go, all right, in these atoms are going to be the electrons. If you're in the nucleus, you're trapped. It's like a prison. You can't go anywhere unless we slam another molecule into you. We don't want to do that because we don't want to create any type of explosion. Okay. So the only thing that can come and go are the electrons. And we know that the electrons have a negative charge. So in order to create an ion, we're either going to add electrons to our atom or we're going to take electrons away from our atom. And this is important because this happens all the time in the body. A lot of our physiological functions, right, for example, in digestion, gas exchange and whatnot, we are going to see the movement of these ions, right, in and out of cells, or actually occurring on cell surfaces when certain metabolic processes or chemical or physiological processes are occurring. So it's important that we have these ions in ready supply in our bodies. So you'll notice a lot of sports drinks like Gatorade, they load up, they advertise their drink as, oh, this is got lots of electrolytes. And electrolytes is a fancy word for certain types of elements that can conduct electricity. Okay, so in our sports drinks, they load it up with potassium. Potassium is a very important element that you have to have in your body. And unfortunately, you lose a lot of it when you sweat. Okay, but you need it for the proper functioning of the nerves, proper functioning of your heart. All right, and so speaking of the heart, if you get a substantially large dose of potassium, right, that could kill you. Right, potassium is one of the ingredients in the lethal injection drug in which they used to give to inmates here in South Carolina. And if you give a large enough dose, it can damage the heart and you can kill the person. Okay, so let's talk about the different types of ions. The first type of ion is going to be, okay, a cation ion. So if you look way down here at the bottom, cation ions have a positive charge. How do I remember a cation ion? Easy, easy, easy. Okay, I had someone tell me once that cats are nice and fluffy and furry. All right, if you're into cats or whatever, or a cat person. And so you get a positive feeling about that cat. Okay, so cation ions are ions that have a positive charge. So that means in order to have a positive charge, that means that that element, that atom has to have lost electrons. Because remember, electrons have a negative charge. So if an electron leaves, it takes its negative charge with it. The protons are still trapped in the nucleus. They can't leave. So they're keeping their positive charge. So if you have 12 protons and 12 electrons, then one electron leaves. Now you have 12 protons and 11 electrons. Subtract the electrons from the protons, and that gives you a +1 value. Okay. Sodium is one of these cations. It wants to get rid of an electron, and when it does that, it reaches that chemical stability. Let me show you. Here you can see, don't pay attention to all this other stuff. Just look at this guy right here, sodium. Here you can see sodium in the shell model. Look to the valence shell. In sodium, there's only one electron that sits in that valence shell. And sodium thinks, hey, you know what? If I get rid of this electron, then this outer shell will disappear. And then the next shell in, which is the second shell, will become my new valence shell. And it'll have 8 electrons in it. And that'll make me chemically stable. And I'll be happy. So I'm going to want to get rid of that electron. So my valence shell can have 8. Problem is, when I get rid of that electron, I have one more proton than I do electrons. So therefore, I have a positive charge. And that's why we write sodium Na+. If it lost 2 electrons, then we write it sodium Na2+. There's no number in front of the plus sign or in front of the negative sign. It's always understood as 1. We're going back there. So I didn't tell you, we gave this a rule, okay? We named a rule after this concept of having 8 electrons in the valence shell. And we call that the Octet Rule, okay? So these elements, these atoms are going to try to fill their valence shell. And it can do so by either losing 1 or more electrons, gaining 1 or more electrons, or even sharing electrons with other elements, so it can have 8 electrons in its valence shell. So we call that the Octet Rule. All right, the tendency of that element or that atom to fill its valence shell. So it has 8. Okay, Octet Rule. So this is what we're talking about when we're dealing with sodium. It's got 11 protons, 10 electrons. Subtract the electrons from the protons. That means we've got a charge of +1. +1. Okay. So of course that's a cation. What about the other type of ion? An anion. A-N-I-O-N-S. All right, anions. So if you lose an electron and you become a cation, but if you gain an electron, then you become an anion. So we'll use chlorine as our example. Okay, so chlorine has 17 protons on the inside and actually 17 electrons in its valence shell normally. Not in its valence shell, excuse me, and 17 electrons overall. So when we look at our picture here, you can see in our diagram how its valence shell has, count it with me, 2, 4, 6, 7. 7 electrons. All it needs is 1 more electron. And when it gets 1 more electron from somewhere, then it fills that valence shell. And now, all right, it has that chemical stability that it wanted. But now it's gained 1 electron, still has the same number of protons at 17. It's got 1 more electron at 18 electrons. Now we give it a negative charge, and so it's an anion. So when it gains the electron, all right, it now satisfies that octet rule. By doing so, it now has a -1 charge. Okay, so anions are ions with, you need to know this, negative charge. And if we have ions, okay, that have more than one type of atom, we call those polyatomic ions. And we see those a bunch in the body, okay? Bicarbonate is a huge, important polyatomic ion. We use it for buffering. Keeps our acids and bases in check. All right, so I just talked to you about positive ions and negative ions. Well, have you ever heard of the term the opposites attract? You've seen a magnet ever? Okay, we used to mess around with magnets when I was in middle school, elementary school, bar magnets specifically. And those bar magnets have a north pole and a south pole. And so if you're messing around with the bar magnets and you're pushing them against each other, and if they stick to one another, then you know that a north pole has actually been attracted to a south pole. They're opposites, but if you try to push two north poles into one another, they'll repel each other. I want you to think of ionic bonds similar, okay, or ions similar to that. So two cations will repel away from each other because they have the same positive charge. Two anions will repel away from each other because they have the same negative charge. But remember the saying, opposites attract. If we get a cation and an anion, all right, one is positive, one is negative, they become attracted to one another. And those attractive forces, we call those electrostatic forces. So that's how we stick cations and anions together through these electrostatic forces, and we create ionic bonds. Let me show you, okay, on the next slide here. We're going to talk about table salt, sodium chloride. Na is sodium, Cl is chloride. So what we're going to see is that sodium, remember, sodium only has one electron in its valence shell, whereas chlorine, has 7 in its valence shell. So sodium wants to get rid of one. Meanwhile, chlorine wants to gain one. So when they do, we're going to actually create what we call a lattice crystal structure. That's an ionic compound. So it's going to look like this. Here's our sodium atom right here, all the way to the left of the screen. We see it donates its one electron in the valence shell, gives it to chlorine, and now has become a cation. Meanwhile, chlorine now has become an anion. Well, you know the saying, opposites, a positive charge, negative charge, attract. And so they'll start to glom onto each other and make these ionic bonds, and they'll start to take on this lattice crystal formation. And they'll look something like what you can see here all the way to the right. So ionic bonds are formed through gaining or losing electrons there. So another type of bond that we want to discuss is covalent bonds. Think of covalent bonds like kindergarten. See, in kindergarten, I learned how to share. Sharing is caring. So in kindergarten, I learned how to share, and that's what covalent bonds do. They're the kindergartner of molecule bonds. So in this situation, we're going to see electrons being shared between two or more, this is important, different elements. Two or more different elements. So carbon dioxide, carbon and oxygen, those are two different elements. They're going to form a covalent bond. Whereas molecular oxygen, you can see here, O2 are not different, okay? So they will not form a molecular compound. All right, so let's see a quick question here. Could an ionic bond form between two cations? Feel free to type in yes or no into the chat bar. Could an ionic bond form between two cations? Remember what I said, opposites attract. That's my hint. Absolutely correct. No is the correct, I can't talk tonight. No is the correct answer. Okay, and the reason why, come on, there we go. Positively charged cations and negatively charged anions may form ionic bonds with one another, but a cation and another cation cannot form the electrostatic interactions needed. They both want to do the same thing. Yes, you guys, great job. Okay. So now that we know the different types of bonds, ionic bonds, all right, covalent bonds, okay, we have ionic molecular compounds. All right, let's discuss how we're going to write this stuff down. We got to figure this stuff out. Okay, so there's two ways. So when we're, as chemists, we have to write out chemical formulas. All right, most of the time we're going to use the molecular. All right, sometimes we'll use the structural. So I want you to think of the molecular formula like the recipe for brownies. Okay, so when you look at the box, you're seeing them list off the ingredients and how much of the ingredients. So molecular formula is the recipe. It's going to tell you, all right, what the ingredients are. So the type of atoms, is it carbon, is it oxygen, instead of eggs and flour and butter and milk, okay? And it also is going to tell you how much. I like to use, the carbonic acid is shown, well, I'll just show you. Carbonic acid here is showing you, here's the chemical formula, all right, or the molecular formula. H is telling us it's hydrogen, C is telling us that it's carbon, O is telling us that it's oxygen. And then the 2 behind the carbon, as you know, is telling us, all right, how many hydrogen there are. The 3 behind oxygen is telling you that there's 3 oxygens. Since there's no number behind the carbon, it's understood as 1. So that's the molecular formula for carbonic acid. Now, a structural formula tells you everything that the molecular formula does, but it also shows you how we arrange or the position of all these atoms for this molecule. Okay, so in this picture here, you can actually see this literally is how carbon dioxide looks. The C is in the middle, and then oxygen is on either side of carbon, exactly like that. Okay, whereas if we were talking about the structural formula for water, okay, water looks like this. There's the oxygen, it's got 2 little legs hanging down, all right, and then there's a hydrogen at the end of each of those legs. It looks like that. So it looks almost like an upside down V. So the structural formula allows us to see, all right, for the actual arrangement of these structures here called isomers. And what an isomer is that you're going to see that there's certain molecules or compounds that are going to have the same exact molecular formula, but their structural formula will differ and how everything's arranged. So let me show you. I always got a picture for something. Let's talk about glucose. Glucose, galactose, and fructose. Those are sugars. These are sugars. So if you notice here, they all have the same exact molecular formula. C6H12O6. Go all the way across. You can see it. They're all the same. So what does that mean? That means that these molecules have the same ingredients, the same number of carbon, just so their recipe, all right, their brownies are all going to have the same ingredients here. But if you notice here, when we talk about the structural formula, if you go all the way to the right-hand side of your screen here, you'll notice that fructose, all right, looks different. It's got a ring. All of them have a ring. Okay, glucose, galactose, and fructose all have these ring structures. But the fructose has what we call a 5-carbon ring. It's a pentose sugar. Galactose and glucose have 6 carbons in their ring, and that makes them, all right, a hexose sugar. Okay, so that's pretty obvious, the difference between fructose and fructose and glucose and fructose and galactose. Now, glucose and galactose are very similar, except if you notice here, carbon 4, right? All we did was flip-flop the hydrogen on the glucose carbon 4, and we just moved it into a different position. Hydroxide group, we just moved it to a different position. And so that subtle difference gives us, all right, an isomer. And isomers doesn't mean they always will, but they can have different chemical properties. They can behave differently because of that structural formula there. So what information about a molecule is gained by a structural formula? All right, the structural formula shows you the arrangement. And that differs from a molecular formula because even though both the structural formula and the molecular formula show you what type of atoms are present and how much, all right, it does not show you the arrangement. And that's important. You need to know the arrangement. All right, so let's talk about covalent bonds in a little bit more detail. All right, remember what I said. First thing, when you think about a covalent bond, you're thinking of a bond in which there is sharing going on. So we're sharing electrons. So in this situation, all right, both atoms that are going to be sharing, all right, electrons, they both require those electrons because they both want to fill their valence shell. That's their goal. Their goal is to fill that shell to satisfy the octet rule. And so you will usually see this occur in atoms that have about 4 to 7 electrons in the valence shell. And if you notice, look at these guys. Hydrogen, oxygen, nitrogen, carbon. Those are the 4 most abundant major elements in your body. And so they're going to undergo covalent bonding. So that means they all want to share. They're greedy too because they want an electron or 2 or more to fill up its valence shell, but they're going to share. So there's a certain number of covalent bonds that specific atoms can form, and it depends on how big the atom is. All right, so the simplest type of bond that we're going to see is going to be one covalent bond that occurs, all right, between 2 hydrogen atoms. Remember what we said, remember the atomic number for hydrogen is 1. It means it has 1 proton and 1 neutron. And it will all, since it has 1 proton, protons and electrons are equal, so it'll have 1 electron. So here is our hydrogen atom right here on the top left corner of our screen. And you can see it's got this 1 atom, but remember, that first shell can hold a maximum of 2 electrons. So it would like to have another one. And so what it does is it floats around and it finds another hydrogen atom. And then see what happens? Now they both share these 2 electrons. So they're drawn towards one another. And so they both now managed to satisfy, all right, that first orbital's valence shell requirement of 2 electrons. So they're sharing. Okay. Oxygen is interesting enough that it needs 2 electrons to fill out its valence shell. Okay. So that means it can form 2 covalent bonds, and it does so here with water. You can see here with the water. Okay, oxygen has 6, so the oxygen electrons are indicated by these red dots, and the hydrogen electrons are indicated by the blue crosses or X's. And so oxygen is going to look around for 2 hydrogen ions, or excuse me, 2 hydrogen atoms, and then again, they'll all share these electrons in their outer shells. And then, like I said before, it depends on what we're dealing with. Nitrogen, it can form 3 bonds, and carbon can form 4. And we saw that here on this page with methane. Cow farts. You see the carbon there in the center, and then it's got 4 hydrogen atoms. And they're all sharing. And now they've all satisfied filling up that valence shell. So for covalent bonds, all right, you can form either a single bond, a double bond, or a triple bond. Triple bond has a lot of energy in it. So if you snap a triple bond, you're gonna get some energy. It's good stuff. Okay. Single bond has the least amount of energy. So when we're talking about a single, double, and triple covalent bonds, it's just basically telling you, all right, how many pairs of electrons are being shared, all right, between the atoms of the covalent bond. So a single covalent bond has one pair of electrons. A double, we're seeing now a sharing of two pairs. A triple, we see a sharing of three pairs. Okay. So I'll show you those pictures here. So there's the single covalent bond at the top, two electrons there shared between the two hydrogens. Right, and you can here's the diagram, and then here's how we draw it out. Looks like two H's with a hash mark in between. And then we talk about a double covalent bond. Oxygen loves to do this, right? So now we formed a double covalent bond. That looks like an equal sign. And then finally, we get our triple covalent bond, which is just saying we have now shared three pairs of electrons. And we draw that with three dashed lines. So again, we can satisfy this octet rule in different ways. All right, for example, if you look at methane, okay, carbon is decided, all right, it has options. I like to have options, especially when I go to a restaurant. Well, guess what? Carbon's the same way. It likes to have options too. So it's going to satisfy that octet rule, you know, one way or several other ways. It can form 4 single covalent bonds, as you can see here, to form methane. It can form 2 double covalent bonds, as with carbon dioxide. All right. And you can see all these different ways in which it tries to satisfy that octet rule. And in some cases, it can form 2 single covalent bonds with 2 of the same type of atoms. And then again, there's a variety. If you notice here, this carbon has 2 single bonds with hydrogen, a single bond with oxygen, and a single bond with another carbon. So it likes to get out and mingle a little bit. So keep in mind that it gives us a little bit of diversity. Later on in this course, we're gonna talk about the carbon skeleton a little bit, not so much in a lot of detail. We'll briefly mention it when you get more into the metabolism about hydrocarbons and whatnot. But I want you to understand that carbon is a very important element because from a chemist's standpoint, if a molecule has carbon in its molecular formula, it is considered to be organic. So if you're looking at a molecular formula of something and you see a C in there somewhere, you can say that's an organic molecule. Plastic is an organic molecule. I got into an argument with a math teacher about this when we were talking about what's considered to be organic and what's considered to be inorganic. And I knew I was right because I learned it in organic chemistry. And because I teach it too, but they had to Google it. They looked it up, and at first it didn't show the answer, so he was kind of celebrating in my face, which is fine. I said, we'll go to a chemist's website, and he did, and I was much more humble. But anyways, so when we talk about these carbon skeleton formations, there's a couple different ways it can do it. We can do it, all right, as a straight chain, and so you can see, all right, basically, when we're talking about a straight chain, that means we've just strung a bunch of carbons together and some other molecules, and then there's just branches of molecules that come off. And so it's basically a straight chain here. Or we can have a branch chain, where you can have a branch of carbon coming off and maybe another branch of a carbon coming off. So you can see how it's not one straight chain. You can see that there's several carbons coming off in one or another direction. Or we can have those ring structures that we saw with fructose, galactose, and glucose. Okay. So again, these different types of arrangements give certain types of chemical properties to whatever it is that we're talking about. All right, so one other thing about covalent bonds. All right, I want you to understand that not all elements are the same. Some are more selfish than others, okay? So there's this term that you can see in bold here on the screen. It's called electronegativity. And its definition reads relative attraction of each atom for electrons. And what I see is selfishness. Basically, what that definition should really say is certain atoms are more selfish and they want to hold on to the electrons more when they're sharing. So it's like that little kid that has something that it doesn't want to give up, like food or a toy. You go to reach for it and it pulls it closer. So now you're grabbing it and they're grabbing it, but they're pulling it closer to them. That's what electronegativity is telling us, that certain atoms will have a stronger attraction for the electrons that they're sharing. So we're going to see when we're talking about electronegativity, all right, basically there's two types, nonpolar and polar covalent bonds, and it depends on which element or atom is more selfish and where most of those electrons are going to be found. Now, if they are the same element, so let's say it's two oxygen, right? Then they're going to have an equal attraction for the electrons. So they're both equally selfish. So because of that, then we refer to that as a nonpolar covalent bond. But now when we see that some of these molecules, all right, are not sharing equally, we call that a polar covalent bond. So carbon dioxide, well, now I don't want to use carbon dioxide. So like I said, oxygen has that, which I won't even draw that out. But water, perfect example. Water, H2O. Here's the oxygen, and then our two hydrogens. Now, oxygen is selfish. So what's going to happen is that the electrons that it's sharing with these hydrogen atoms, it's going to pull them closer to the oxygen. So that will make the oxygen more negative. And it makes the hydrogen area of this molecule more positive. So it creates like a polarity, a positive and a negative pole or end or part of this molecule here. So when we're looking at the periodic table here, okay, with our rows and columns, as we move from the left to the right, okay, electronegativity increases. So the elements on the left side of the periodic table are less selfish, and the elements on the right side are very selfish because they have a higher electronegativity and they're going to pull the electrons closer to themselves. And as we move from the bottom of our periodic table up to the top, electronegativity also increases. So that means, all right, that the elements at the top of the periodic table are much more selfish than the atoms or the elements at the bottom. So how do we relate this to living organisms? Well, look at those four major elements in your body: hydrogen, carbon, nitrogen, and oxygen. Like I said, oxygen is very selfish. It is very electronegative. All right, hydrogen is not. Okay, so keep in mind how that electronegativity results. So because those electrons have that negative charge, wherever we find those electrons to be residing, it's going to confer or develop what we call a partial negative charge, like we saw in water. Okay, oxygen was up here, the hydrogens were down here. And so oxygen is hoarding those electrons, so that makes the part of the molecule closest to the oxygen more negative. And then where our hydrogen ions or atoms are, they'll be positive because they have less of an electronegativity in that area, so they become partially positive. Now, of course, there's always exceptions to the rule, right? When we're discussing polar bonds, right? In this case, when we're seeing the formation of carbon and hydrogen bonds, we do not see, all right, that unequal sharing. Okay, that is the exception, carbon and hydrogen. Quick sip. Oh my goodness, you guys are doing great. We won't run as long today. Yay. All right, so let's switch gears. After class tonight, most likely when I'm done, I'm going to go downstairs to the kitchen and I am going to probably have to wash all the dishes in the sink. The relationship between my wife and I is that she cooks because she's a wonderful cook. She loves to do it. I'm lazy. I'll do it if I have to, but I'm not as good. So because she does that, I clean. And I'll tell you what, when I'm cleaning, if I can't get things off right away, all right, even with a little elbow grease, I like to soak. And I know that there's some of you out there that like to do the same thing. I'm a soaker. Guess what I soak it in? I soak the pot or the pan with some soap, but also water. Water is literally the universal solvent. And what does that mean? The universal if something's a solvent, that means you'll have things dissolve in it. So when we're talking about water, you need to understand we have substances that will dissolve in water and substances that will not dissolve in water. And so you need to know these qualities of what makes something able to dissolve in water and what makes something not dissolve in water. Non-polar molecules do not dissolve in water. All right, so we call those hydrophobic. And you've seen this before. If you've ever boiled water to cook pasta and you add a little bit of olive oil or whatever type of oil that you like to use, and you'll see the oil float on top. Right? You'll see that at the gas station, there's a puddle there. You'll see like a kind of a sheen there, right? And that's because the oil does not dissolve in the water, and that oil is non-polar. Now, substances that do dissolve in water are going to be polar molecules and ions. Okay, so they will dissolve or disperse in the water. We call those hydrophilic. They love the water. That's important. Your blood plasma, the majority of your blood plasma, over 92% of it is water. And in that blood plasma, you have dissolved ions, okay, which is nice. So when they do a blood work on you and they check like your calcium and your sodium and your potassium, guess where that is? Those are the ions that are dissolved in your blood plasma. And they're looking at those. Booyah! Bet you didn't know that. So water is a neutral solvent. What does that mean? Well, we're going to start talking about acids and bases here, but I need to talk to you about this phenomena first that occurs with water. Water is kind of funky. It likes to disassociate from time to time without any warning. It will just spontaneously do this on its own. What does disassociation mean? Look down here. Here's water, H2O. It'll break apart or disassociate. And when it does so, it forms ions. And we know what ions are now. Okay, we know it's a charged element. It's a charged atom. So you'll see here, water will break apart and it will form, all right, a hydrogen ion. And this molecule here, which is called a hydroxide ion, right here, OH negative. That's called a hydroxide ion. Okay, so when this happens, all right, when this phenomena happens down here at the bottom of the page, then, all right, these guys, this hydrogen ion will interact, it can interact with a water molecule, okay? So it'll be transferred over to a water molecule and it'll form hydronium. But check it out. It still has a positive +1 charge to it. And then we've got our hydroxide ion here. We just moved it up here in this formula. But the good news is we still have a negative charge. So we have one positive charge, one negative charge. They cancel each other out. That's what we're talking about here. Equal numbers of positive hydrogen ions and negative hydroxyl ions are produced. So this phenomenon, we have equal positive and equal negative ions that are produced. They cancel each other out. That's why we say that water is neutral. Boom. Mic drop. Done. If anything, I want you to pay close and strict attention to that right there, that formula. Boom. That water disassociates and you get one hydrogen ion and one hydroxide ion. One is positive, one is negative. They'll cancel each other out. And so water remains neutral. Neutral. Because that gets us into acids and bases. You need to know about acids and bases because there's so many physiological functions in the body that are going to have a role with this. Acids, for example, hydrochloric acids in your stomach helps to break down proteins. Proteins are a son of a gun to break down. So we need help. And that hydrochloric acid actually will help to activate certain inactive enzymes to also help them break that stuff down. You get to learn about that all in chapter 26. So let's define what an acid is. So an acid is going to be this chemical that we're going to add to water. And when we add it to water, that chemical is going to disassociate. It's going to break down. All right, I like to use hydrochloric acid in my examples. HCl, okay, is going to break down into a hydrogen ion, and a chloride ion. So behind the hydrogen ion, there's going to be a plus here. And then behind the chloride ion, there's a negative. Okay? So that's our formula. Hydrochloric acid, when it disassociates, it gives us, okay, it gives us a hydrogen ion. And we're going to rename that hydrogen ion, guys. We're going to give it a different name. You can call it hydrogen ion still if you want. And we get what's chloride with a negative behind it? That's an anion. It's a negatively charged ion. Okay. So with an acid, when we add it to water, it's going to give us a hydrogen ion. Another name for hydrogen ion is called a proton. Don't ask me why. Don't ask me why. So therefore, we call acids proton donors, which means when we add an acid to something, to the water, and it disassociates, it's going to donate that hydrogen ion, all right, to the water. So an acid that disassociates quite easily, we're going to see a large increase in the concentration of all these hydrogen ions just floating around. So the easier it is, or the more disassociation of hydrogen ions, all right, will occur in stronger acids, hydrochloric acid, for example. And then when we see an acid added to water and we don't see as much disassociation, that's a weaker acid. I have to use hydrochloric acid at work and they tell me I have to add it in the water and not the other way. Yeah, you know, it's funny. Yes, it does. And it's because of the solubility of it. When I took chemistry in high school, that's one of the things I do remember. You always had to add the acid, all right, to the water and not the water to the acid. You're absolutely right, because it can have a violent reaction depending on what type of acid you're working with. But yeah. Okay, so that's an acid. Well, what about the other structure? Not structure. You got it. All right, bases. So if you have an acid, all right, and that's a proton donor, All right, let's talk about what a base is. Okay, bases, I want you to think of a base as a hydrogen ion sponge. It's going to go around. If you add it, all right, so we added, let's say, hydrochloric acid to some water, and it did its thing. Now I'm going to add some base to that same beaker with the water and the beaker that I added the hydrochloric acid to. So now I'm going to add this base to it, and it's going to go around, and it's going to go up and soak up all those hydrogen ions. So it's going to accept the hydrogen ions. So that's why we call it a proton acceptor. It goes around just sucking everything up. So it's going to decrease the concentration, how much hydrogen ions or protons are just floating around. So think of it like a paper towel. It's got great absorption powers. So the more absorption we get, the stronger the base is. Okay, the less absorption that we get, it's going to be weaker. If you look at our strong bases, ammonia and bleach, those are strong bases. They're wonderful cleaners because of this property. Okay, and then these weaker bases, bicarbonate, that's going to be a much needed molecule in your blood because it helps to buffer the blood. And we'll talk about that at another time. All right, so what type of substances release hydrogen ions when added to water? So when I add whatever it is to water, I'll even make it easy on you. Is it an acid or is it a base? You can put your answer in now in the chat bar. Acid or base, feel free. If I could play the Jeopardy music for you, I would. Okay, so what type of substances will release hydrogen ions when I add it to the water? They'll just pop off and float around. Booyah, acids, that's right. Acid, acid, acid. You guys rock. Great, great, great job. Correct. Correct, correct. On point, people. Acids, very good. Okay, well, we made it as far as I want to get for today. I would love to get into pH and neutralization and the action of buffers because that's the good stuff, but it'll take me too long. So I think this is a good place to take a break. Awesome job. What I would like to do, again, if you have any questions, just hold on to them for when we get to lab class. Okay, we'll do that once we get to lab class.